At the start of this series of videos, I mentioned the custom electronics we developed for our micro EV. Well, here it is. This is a custom system we developed to allow us to measure key operating parameters on the EV and relay those wirelessly to the computer in real time for display and logging as the car moves around. At the heart of the system is an ESP32 module from Heltec, which incorporates a microcontroller, display and wireless communications. We program this board to transmit data from the car to a computer in real time. The remaining parts of the system comprise power management, temperature sensing, accelerometer, analog measurements and a pressure sensor. We also included a drive stage for NeoPixel LEDs. Let's take a look at these circuit subsections in a bit more detail. In our power management block, we're using a synchronous buck regulator from TI. Let's take a look at some of the switching waveforms. So this is our power converter running with 1 amp extra load on the output. It's regulating at 5 volts, here's our extra load. And on the input side, we have a power supply to emulate the battery of the car. And we're also measuring the output voltage, which you can see is close to 5 volts. This power converter operates a closed loop control, so you can see as we turn the input voltage up, it dynamically changes the duty cycle to maintain the output at a constant regulated 5 volts. In this example, we take the input voltage up as high as 35 volts, but the converter can operate up to 60 volts. As we go down in voltage, we hit under voltage lockout and the chip protects itself. And then as the voltage comes up again, the chip starts switching and we get regulated 5 volts. Moving on to the temperature measurement section of the circuit now, we want to use thermocouples to monitor key parts of the drivetrain. We used an IC from Microchip, which connects directly to the thermocouple wires and performs the necessary functions to allow the processor on the Heltec board to read temperatures via an I2C protocol. We can monitor the data on the I2C digital bus using a protocol analyzer function on our scope. We can see the bursts of communication 20 times per second. Zooming into one burst, we can see the high frequency clock and data waveforms. Those waveforms are formatted to contain the data we want, which the scope can capture for us. The Heltec module is centered around a 32-bit ESP32 microcontroller from Espressif. This part incorporates two 12-bit ADC cores, which we use to measure the car battery voltage and current. An ADC works by sampling an input voltage and turning it into a digital value. The 12-bit core can output 2 to the power of 12 discrete values to represent the continuous analog signal. So, we get a digital value between 0 and 4095. The more bits the ADC has, the better it can represent the analog value. For the battery current, we need a circuit to measure the current and generate a voltage proportional to this to present to the ADC input. To do this, we used a neat IC from TI, which utilises something known as the Hall effect. When a current flows in a wire, it generates a magnetic field, which we observed in practice in our last video on motors. The Hall effect device measures the strength of the magnetic field near the conductor and provides an accurate representation of this to the ADC. The accelerometer is a tiny little IC from TDK, which incorporates a 9-axis measurement capability. This gives us a 3-axis accelerometer, which we can use to measure the g-forces acting on the car. It also acts as a 3-axis gyroscope and 3-axis compass. Communications with the ESP32 processor is achieved using an SPI bus, which uses 4 digital lines to communicate: chip select, data in, data out, and clock. This allows full duplex communications at a much higher data rate than I2C. Using the scope again, we can see the activity on this bus with the decode of the protocol in real time. Running this circuitry on the car over a 10-minute duration, we begin to capture interesting thermal data for the motors, drive and batteries. A real-time power measurement can be integrated to provide a total energy use, in our case about 5 kilojoules in 10 minutes, around 20 to 25% of the battery. The discharge of the battery over time can be clearly seen, with us starting at 15.7 volts and dropping to around 14 volts. The G-forces the car is subject to are generally around 1G in the X-axis when cornering and 5G in the Y-axis when braking. We did see a G-force as high as 16G during the test, but this is when I crashed into a tree. Thanks for watching. I hope you found this video useful and interesting.